All right, welcome everyone. I'm Greg Luck. I'm the CTO and CEO of Hazelcast, and it's nice to be at an in-memory computing summit. I've been doing in-memory stuff for a very long time. Years and years and years ago, I created an open source cache, in-process cache called cache that some of you might have used through the years. And then I was at Terracotta, and then I've been at Hazelcast for 4 years. Hazelcast is an in-memory data grid, quite similar to GridGain and Ignite. And we embarked 3 years ago on building a fast big data platform. So we went a little bit of a different direction to GridGain, who've kind of been turning their thing into a database. We've got a brand new open source project came out in February called Hazelcast Jet. It's Apache 2 open source, and it is aimed at the fast big data market. So what is it? It's a distributed data processing engine. It's built on Hazelcast, so we get a lot of things for free. A lot of things that are very, very difficult to do, we already have solved. And it is a DAG-based system. So why? So why would we do this? And the answer is it was over a beer with a guy called Chris Wenzel, and he built the the way all good ideas start. So he built the cascading framework, which is used by Twitter and some others on top of Hadoop. And he had wanted for years to have something much, much faster. So he's like saying to me, you know what, I'm pretty sure you guys could do it faster. And I said, okay, well, let's find out. So we did. The answer, apples to apples, word count, starting with HDFS, 10 nodes in our lab, is that we're more than 10 times faster than Hadoop. So yes, he was right. And that was the primary motivation. We thought that it should be possible for us to go in and build something from the ground up that would be way faster. And I've got performance numbers I'll share with you. We are the fastest in industry. And not by small percentages, by multiples. Now, Hazelcast has 36 million phone homes per month. It's an incredibly widely used piece of software. That's increased back in 2014 when I joined Hazelcast, it was only 4 million. So people keep finding more and more ways to use the in-memory data grid. Now, an in-memory data grid has partitioned, it's complicated, but simplifying it, it's a partition cache that runs across a grid of nodes. But they also get used for compute. And where that compute works best is where the compute is on data that's on the node. So you run the compute where the node is, it's in situ processing, and it works great. Now, it's possible combining the executor service and entry processes to build your own sort of IoT or batch processing or even a stream processing system. You can kind of build that yourself with an in-memory data grid, but often it relies on just super fast gets and puts to make it work. It's kind of a little bit of a misuse of Hazelcast, and I would estimate of our commercial customers, probably about 20% are actually using us this way. So kind of the motivation was, look, these people are trying to solve a problem, let's give them a better way of actually doing that. Now, we also had Java 8, and Java 8 kind of came along with java.util.stream, which must be the most horribly named package ever, because what it doesn't do is streaming. It's actually batch. So what we've done with Jet, amongst other things, it's a distributed version of java.util.stream. So if you know how to write Java 8, you can fire up Jet. You can do a 5-minute productivity test and see what it's like to run those things distributed. And you know, I thought this was like relatively easy for us to do, and it hasn't been too bad. We've got a team of about 6 people who've been working for about 3 years, so that's reasonably easy compared to most things. So we are aiming for the same use cases that everybody else is aiming to do. It is both batch and streaming. It's not micro batch. It's not micro batch. You can update your output with an input change of just one item. It's all about how you configure your windows. What we've done here is we've got, and I'll go into all the adapters that we have, but we've got all the common adapters that you can read in from streaming and batch sources. Now, if you've already, where this works best is if your data is already in Hazelcast. If it's already in Hazelcast, then it comes in super fast, and we're actually running the computation on the same nodes where the data is, so we're getting all the benefits of in situ processing. You can enrich by doing joins against Hazelcast or other sources, and you can write out to sinks, or you can write out to Hazelcast. So the kind of sweet spot of this is that if you can combine the in-memory data storage and the processing in one thing by using the two together. That's where this really explodes, as you'll see in the performance numbers. Okay, so just going to run you through kind of the theory of what we're doing. Most of this is common to DAG-based systems. So what we've built is a way of actually processing data by using all the CPU cores. Jet will use all the cores on your system. How do we efficiently do that? Well, the starting point of computation in languages like Java is that things happen serially. And so in the old world, when you did this would actually execute serially. So it's a single thread that's executing this. You've got steps that happen after other steps. So it doesn't matter how many cores you've got on your system, this code is not going to use those. So one way to get started on using more cores is if we've got a pipeline of steps, tokenize and aggregate, you can actually run each of those steps, each of those vertexes you can run on separate CPU cores. And there's a, that's also still single-threaded. This is the concurrent one. So if you have concurrent queues, you basically have a queue before each thing, then they can run at their own speed. You run them on separate cores. So we have single producer, single consumer. It's one of Martin Thompson's patents, and we use that. Now, there's some of the steps can be parallelized. So this is where we parallelize. And so tokenize is a great thing that can be parallelized. If you break the text into lines, you can use multiple threads. And then we can also parallelize the aggregation step. So the way we would do that is aggregating by individual words. Now at the moment, we're all on a single machine. So each one of those orange boxes, we've now got 4 threads that can be running in parallel. And you can take this and you can increase this to the number of threads that you have on the box. And in fact, in Jet, the setting is called parallelism. And but if you don't define it, we will use all the cores for each step. So you generally want to define it down. And then this is what it looks like across a cluster of servers. So it's the same thing, except the yellow dotted lines are actually network hops. So this is a distributed partitioning scheme. And then with this design approach, you can use all of the cores on a single machine, and you can use all of the cores on a cluster of machines. And so when we do our word count benchmark with our 10 server perflab, that's what we're doing. And we believe we're doing it more efficiently than others, which is why we're faster. And that's what we do. So that's the processing steps. Now, obviously, we're not entering a space that's not occupied. I mean, Hadoop's been around for what, more than a decade? Spark's been around for a long time. We've got things like Flink. We've got Kafka streams. I mean, there's a lot of things happening. The way I see it is that you kind of had the era of Hadoop, and then you had the era of Spark, and then I think now it's a much more fragmented world, and we're part of that fragmentation. So I think that people I don't know about you guys in the room, but I think generally speaking, at this point in time, it's possible for somebody like us to come along and learn from what's been done before, apply all these techniques, and try and do something better. And I think there's appetite out there to actually try these different things. So, you know, the way we see ourselves is that we have industry-leading performance. We've got the benchmarks, we've published those, I'll show them to you. You can run those, you can run your own jobs on Jet and see what you find. The other thing is, with such a huge user base for Hazelcast, we want to make it work great with Hazelcast. So that in the Hazelcast data structures, like we want you to be able to use those as sources and sinks, and also for easy enrichment. Now, perhaps the hardest thing that we've found in Jet is to make it simple. Hazelcast is famously simple. We've got a devilishly difficult API. We call it the core API. And we've actually struggled to bring something simple. So 0.5 comes out this week. We think we finally nailed it, and I'll be showing you that API. And then from a deployment point of view, one of the reasons I think that Hazelcast sort of, the amount of usage it's getting has exploded is just the trend towards microservices. So, you know, this like Hazelcast is a 10 meg jar with 0 dependencies. You have no dependencies. So you can take this thing, you stick it in your app server, you spin up your microservices, that's it. It works with every cloud just like Hazelcast does, or you can run it client server. But the embeddability of this, small, lightweight, easy to embed. What we're finding since we released this in February is that people that have been building their own frameworks, not Hadoop users, not Spark users, but within large companies, people, you know, architecture groups, whatever, are building their own. People rolling their own are the ones that have been most interested in adopting Jet so far. So let's look at performance, which we think is perhaps the best reason to try out Jet. So this is word count. Now, the Hadoop numbers are not on here, because if you put the Hadoop numbers on here, you can't see anybody. Everybody else is so fast, you can't see any difference. So let's forget about Hadoop. So we've got, so this benchmark is, as I said, it's our perf lab, 10 servers. It's spinning disks HDFS. So we are blue. So this is megabytes per second. So we are way faster. We are way faster than Spark and Flink. But where this gets really exciting, so let's take Spark 2.1. By the way, Spark has got, on our measurements, Spark has actually gotten slower. I don't know if we test, this is pretty recent, but the 1.x versions were actually faster. So let's say it's doing about 800 meg per second, and we're doing about 2,000. So it's around about 2x or even a bit better than that. But, and this is the key thing, if you combine the two technologies, like with Spark, the second time you run it, you've got things in RDD cache, it's going to be a lot faster. This benchmark is showing everything starting from HDFS. So yes, Spark does caching. With Hazelcast, it's a little different. The idea is that you can be using Hazelcast or GridGain, one of these things, as an operational store. So you're holding the data that you need for your critical transactions in memory. That's where they live. So it's very, very valid for us to say, okay, that's going to be the source of the processing. And we've got some production use of Jet, and in all cases, it's actually running, it's actually computing data that's actually stored in Hazelcast IMAPs. So then you get the green bar. So then that's the true power of this. Now we've got streaming. That was a batch benchmark. We've got streaming as well. Now here what we're looking for is latency. What is the latency as throughput goes up? So we take this up to 5 million operations per second. This is on a 10 node cluster. And you see that we stay flat, whereas some of the other frameworks actually blow out in terms of their latency. Now, question got asked to me, how does this compare to, say, doing word count with java.util.stream on a single JVM? So we actually tested it, and the answer is, you know, almost the first slide, I showed you how if you decouple the stages with single producer, single consumer, it makes it faster. So ForkJoin doesn't do that. We do that. So we're actually faster than ForkJoin on the JDK. That's the second column. Now, if your starting point is to load everything into memory, then java.util.stream is a little faster. But no one's going to do that. So this is very, very quick technology, even as measured against ForkJoin in the JVM. And the team that built this at Hazelcast, they come from the low latency financial services areas like Goldman Sachs, some banks in the UK, things like that. So it's sort of the techniques from Martin Thompson, the techniques from Peter Lorre, these are the techniques that are actually in the code. So I think we're coming at this from already a very, very high performance area, and we're actually adding some of those tricks. Now, before I talked about, I've talked about deployment options. You can do embedded or you can do client server. It's just an 11 meg jar. There's also two choices for how you interact with data that might be in Hazelcast. Because Jet is built on top of Hazelcast, you can actually run Jet as a superset of Hazelcast. We do use some, we do store state. We have our own IMAPs and things that we use inside Hazelcast. So depending on what you're doing, that's a valid choice. And the other one is to run Jet as a separate cluster to Hazelcast, in which case we work remotely. Now, APIs. So these are, as of 0.5 this week, and it's probably like 2 days out, we've got 3 APIs. So our core API is a very, very low-level API where you actually create vertexes and edges and you connect them together. And the folks that are using Jet today have been using that. As I said, people have rolled their own frameworks, expert-level users. Then we have java.util.stream. Now, java.util.stream is the API from Java 8. It's batch only, and it doesn't do joins, and just generally speaking, it's very, very limited. However, we see the value of this in people that are new to Jet actually just taking it for a spin using java.util.stream. So I'll be giving you a code demo in a couple of minutes to demonstrate each of these APIs. And then the other one is this new pipeline API. So the new pipeline API is our new super simple API, which is designed for very, very wide use. It's very powerful. It's not limited, but it is very reminiscent of Java.util.stream, and so that's where most of our code samples are today. And we think with this, we've finally achieved the level of simplicity that we need to make this thing kind of very widely usable. So let me show you some. Let me walk you through some code. This is word count. This is word count using our pipeline API. And you might be forgiven for thinking that that actually looks just like Java.util.stream. That's deliberate. So we, after a lot of hemming and hawing, we came to the position that a declarative, what we needed was a declarative API. So the way this, it's declarative, it's fluent, and it's a pipeline API. Java.util.stream should have actually, the package should have actually been called Java.util pipeline. So what we do is we run this through an execution planner, and then what it does, it actually converts to our low-level language, the DAG, and then it's executed. So you're not losing any power. It's even possible to actually convert a pipeline to a DAG and then further manipulate it. So let's run the code sample. So by the way, we at Hazelcast, we're big believers in code samples. This is just called Hazelcast Jet code samples up on GitHub. And I'm just going to stay with word count because it's kind of easier just to sort of compare them. So I'll just run that. No, I'm not on the network. I'm on the good old in-memory computing summit Wi-Fi, which is, of course, not working. Okay, let's try that again. Oh, actually, it came up. So I wasn't on the network. Hazelcast wasn't able to form a cluster. And then when I fixed the network, it actually popped up and then it ran. So what you'll see is this here is the DAG that's being executed. So it specifies vertexes and edges. And then it runs the word count. It's actually using a 2-node Hazelcast cluster. So some sort of things to point out. In Hazelcast, you have a job. So the way you Hazelcast Jet, the way you kick things off is with a job. You then submit. Here I'm actually submitting a DAG. I can actually also just submit the pipeline. So you can either submit a pipeline, you can submit a job, or you can submit java.util.stream. So I'll just run that again. Two-node cluster, takes time for the cluster to form. This is just a startup thing. Normally the cluster is left running. With Hazelcast Jet, by the way, with this job concept, each job has an isolated class loader, distributed class loader. So you can actually run. We've tested up to a couple of thousand parallel jobs running in the cluster, which is something that other frameworks can't do. Okay, so that worked. So now if I now talk about java.util.stream API, this is java.util.stream as you know it. We did have to create, we did have to extend it to create distributed versions of the operators. The way the API looks, if I show a code sample, it's down here. It's the core API. Okay, so this one is word count. We've got two forms, word count from HDFS and word count from map. So this is the key part here. You can see it looks almost identical. Just as before, we start off by creating a new Jet instance. All right, so I'm going to run this. So the idea is to get people comfortable with Jet by using java.util.stream, and then to move, once you're ready, to kind of move beyond the simple things that you can do with java.util.stream to then go to our pipeline API. So once again, for execution, this gets converted to a DAG, as you can see there. So we have our execution plan, gets handed out, and then it runs. So Jet, as far as we know, there's no maximum size for the number of servers and the number of CPUs that you can actually run. And there's no other limits that we're aware of in the architecture. Okay, so that's the next thing is the core API. So this, I mean, what we did is we started off building the engine, and the engine was based on a DAG, and we kind of needed to, rather than worrying about easy to use APIs, we basically sort of built things at that low level. And so as you can see, the starting point here is to actually create a DAG. So you create a DAG, and then you define your vertexes, and then you define your edges between the vertexes. You can define things like whether execution is local, the level of parallelism, and so on. And if you take word count and you're trying to, if you compare this to the declarative form, this is actually quite hard to get your head around. You kind of pretty much, to work at this level, you need to take a computation and actually kind of break it up into pieces and sort of put the pieces on a whiteboard and draw the vertexes and edges and then kind of figure out what you need to do. So it's quite difficult. But you don't need to do that anymore. Well, in a couple of days' time. Let me show you an example that uses the core API, the same example. So then this is word count in the core API. And so this is similar to what I just showed on the screen. You do all these steps. So now let's run this. So same thing, we're just running a 2-node cluster on my machine. Then once the cluster forms, the job will be created and submitted. There's the DAG. This time we didn't convert to a DAG. This time we manually built the DAG ourselves. So this gives you that fine control. Now, and I think there will continue to be a place for sort of expert users to actually use this DAG API. Now, let me now jump into the Jet architecture. So this is a block level diagram that shows Jet. We've got the APIs that I showed you, the pipeline API and the stream API. We've got a connector level, so a source and a sink. We've got sources and sinks. They're streaming or batch. Then we've got the core API, and there's kind of some key. Let me come up. Do you use this thing? Hello. There's at the bottom we've got Hazelcast. So we're getting all of those services. We're getting the deployment to all the different environments, networking, the cloud discovery, and then all the partition management. And they're also getting use of the data structures. We use Hazelcast maps for storing our job states. Then we've got job management with lifecycle, resource distribution and deployment. Then we've got execution, fault tolerance, and then the core API built on top of that. Now, to go from an abstract DAG to what we actually execute, the concepts we execute with, for us, a vertex is a processor. And then processors have edges. Now, the unit of execution is actually what we call a tasklet. Now, everything in Jet is written in Java code. Hazelcast itself supports 6 or 7 languages. We are planning on adding extra language support, There's no reason why we can't do that, but we just haven't got to it yet. Now we've got a whole bunch, the processes that we've got built already are most of what you need, or all of what you need. But it is also possible to build your own processes. So we've got map, filter, flat map, group by key, co-group, hash join, and many others. Now, when we deploy to all of our nodes, key thing is that each node runs the whole graph. So all processes are present on all nodes. We apply back pressure between vertices, and we have control over the thread count that's used. Now, the key thing with the tasklets is that they use we call it cooperative multithreading. So the idea is that a tasklet does a very, very small amount of work, typically less than a millisecond, and it spins around and round. And there's work stealing between tasklets. So on each machine, you've got processes, you've got tasklets that execute the processes. They spin around and around, and normally they're going to be executing the same processor, so there's no context switching. This is kind of the key thing that makes Hazelcast Jet very, very fast. For this to work, they've got to be non-blocking. Now, Java doesn't give you strict control over core affinity, so it's just by keeping the core very, very busy doing the same thing that we almost guarantee core affinity. Now, if tasklets run low on work, they will gradually back off. They'll exponentially back off, actually, but to a maximum 1 millisecond, therefore guaranteeing low latency of the system when data and work arrive. So the edges, I talked before. I think I've mentioned Martin Thompson's single producer, single consumer about 3 or 4 times now. But these ideas, these low latency programming ideas that have been popularized by these guys are really deep in the design of Jet. So it's weight free on both sides, very efficient. We have back pressure built in. The sources and sinks are a special case where they're actually blocking, so they're non-cooperative and blocking. So bringing it all together, showing what it looks like, there's 2 vertexes. So each of those is a processor, and then on the diagram on the right is 2 threads showing thread 1 and thread 2 on a machine. And those threads will be, you've got each of those as a tasklet that will, you've got different tasklets. The same tasklet is getting executed on the same thread continuously. Depending on the level of parallelism, you can have it as low as a single tasklet per core. This is what makes it fast. Now, by default, if you don't specify parallelism, it will actually default to the number of cores in the system. In terms of edges, there's unicast, broadcast, and partitioned. You can have more than one input that allows co-grouping. You can have more than one output, which allows splitting and branching. Now, edges can be local or distributed. By local, we mean that the processes that the edge is joining are both on the same machine, or they can be distributed. Right, so how do we connect this to the real world? So with all these connectors. So starting with Hazelcast, we've got batch. So batch is where we're just going to read from a map. If you're deploying Jet, and if your map is in the Hazelcast that it's embedded inside Jet, then there's guaranteed to be perfect partition affinity, so that when Jet kicks off and reads, it's going to be reading from the same partition that Hazelcast is using. So that means that you've got a single process. Something that we've done is we've built a new event journal which uses a ring buffer per partition in Hazelcast. Using that ring, it's an in-memory ring buffer. Using that ring buffer, we can get very, very high streaming performance. And so that's new in 0.5. So it allows for very, very fast streaming from iCache, IMAP, and then we've just got the regular Hazelcast API for the batch. Now we've got HDFS. We won those benchmarks that you saw. We won those using our HDFS connector. Kafka is very, very important. So with Kafka, Kafka becomes very, very important for streaming and fault tolerance because Jet is fault tolerant, but to pick up where we left off, we need to go back to the offset in Kafka, which we support. We've also got socket, and we've got batch processing of files, and then another one that's really common in these types of systems is the file watcher. So that's where you specify a directory and a file pattern, and then we just watch and wait for new files to come along, and then we process those. And then you've got custom, so then you can create your own. But this is a pretty strong list to get going with. This, certainly all the use cases that we've seen coming along just use these. Now, stream processing. Stream processing is something that we added. So we added in 0.5 that was released about 4 months ago. So the windows, so here we support sliding, tumbling, and session windows. I'm just going to give you a demo of sliding windows right now. So this one is a stock ticker where we're actually enriching data by joining. So let me just run this, and we're actually using this is actually what's driving this is imagine that you've got trades coming into a Hazelcast map. What we want to do is we want to listen for the changes. So we actually use an event journal on the map. It's using those ring buffers. Highly, highly efficient because there's a ring buffer per partition. Hazelcast by default's got 271 partitions. If that's not enough and you want to throw hundreds or thousands of cores at this, just increase the number of partitions. There's no architectural limit in this thing. Anyway, let's kick this off. So this will start a couple of nodes, and then this is a 10-second sliding window. So we won't get data emitted until 10 seconds has gone past. Now this is a sort of segue onto our handling of fault tolerance. So the way this is configured at the moment is it is with a processing guarantee of none, which means when we kill our second node, you'll see a gap in the data. So there's some stock trades. Now we kill one of the nodes. Now Hazelcast Jet is fault tolerant in that it will pick up the job and continue processing on the single node that's left, but you'll actually be missing some data. So you can see there that it actually jumps to 24. These are sequence numbers. And where we left off was we were at 7s. So there's been a gap and we've actually lost data. But the processing continued. So this is fault tolerance with no guarantee around processing the individual items. So leveraging the IMDG, what we do is the job, each of the jobs, their status is actually stored in a series of Hazelcast maps. Now, Hazelcast maps are high performance, very high performance. When I say high performance, even across the network, we're more than 2 times faster than Redis. They're resilient because the data is distributed with backup copies, and we have, they're also high scalable. You can scale into off-heap, and they can also be made persistent. So we have all of these characteristics just because we're using IMAP. Now, we get automatic re-execution of the job. You saw that when we killed the node. We're tolerant to the loss of nodes. The other thing is that you can also scale the cluster up. In Jet, I talked before about how you can, it's designed to have jobs that execute with their own isolated class loaders on this infrastructure. So what you can do is you can add extra nodes. You can go to 2 nodes, to 5 nodes, to 10 nodes. Now, your current job that's executing won't use those extra nodes, but as soon as you kick off a new job, it'll actually use all the extra nodes. So you can scale up just by spinning up new instances of Jet. So if it's a microservice, you can do that without taking a hit scheduling downtime. And then because maps are persistent, you can also fully recover from a lights out event. If you've got to restart the entire cluster, or you have a lights out event in the data center, if you have the maps configured to be persistent, then it will actually come back and actually restart and reload, and then actually kick off the jobs where they left off. So that's our whole story around job management and fault tolerance. Now, processing guarantees. So I just demonstrated for you the none processing guarantee. It does not use snapshots. And now it's fastest. All of the benchmarks I showed you before were the no processing guarantee, but we're also comparing with the other frameworks also running with no guarantee. Now we also, so this is new in 0.6 that comes out, 0.5 that comes out this week. We have at least once and exactly once. So now, and the way that works is we snapshot. By default, it's every 10 seconds. We actually snapshot to the in-memory data grid. So because we're built on top of Hazelcast, we can snapshot to this highly available, resilient, high-performance store. So so I'm going to go and change the code now and actually demonstrate this. So this is the none guarantee, and now I'm going to change it to exactly once. Now, when you're using exactly once, you must use a snapshot. The snapshots are already automatically there. If you don't set the config, then it's set to 10 seconds. I'm setting it in this example to 5. So now let's run this again. So as with the other examples, we're going to form a 2-node cluster. It's going to take some time for the cluster members to find each other and form a cluster. This is just a startup cost. If the cluster's already running and you start a new job, it's instant. Now we're going to wait for our 10-second sliding window. This is a sliding window, so we're not going to omit data until we accumulate 10 seconds worth. You can actually see some log messages about snapshots there. There's the second one. Right, and then we're going to kill a node. Oh, hang on. Did we already kill the node? Oh, I wasn't watching. We killed the node. So you can see there, we were at 7s. Then we killed the node and interrupted it. I was looking at you guys, and then we picked up and see it went straight to 8s. So there was no loss of data. So that's the exactly once guarantee. We're still, we've run some benchmarks on this. We've compared ourselves with the competition. We are at least as fast as they are. Interestingly, we've actually hit some garbage collection noise in doing our snapshots. So we're going to be doing some more work on this in 0.6. The ideas that we're going to explore are using the off-heap capability of Hazelcast. That's our usual technique for dealing with garbage. But we're also thinking that what we might need that's better than just using a plain map is to use an append-only data structure. So build a new data structure in Hazelcast that's actually sort of more ideal for this. So watch this space. And we have 4 minutes and 51 seconds to go, and I'm ready for questions. All right, gentleman in the stripy shirt. So the question is, if we snapshot, we snapshot periodically, so what happens? So it's just like Spark, we just go back. We go back to where we were and then snapshot from that point. Now, if we're coming from so this is 10 seconds. So in my actually, I had it coded to 5 seconds. But let's say we snapshot every 5 seconds and we're streaming. Remember that data loss is only a concern for streaming sources. For batch, you can actually it just picks up where it left off. But for streaming, you've lost that data. So true fault tolerance or the guarantee is only supported for streaming data sources where you can go back, you can rewind back. Now you can, with Hazelcast maps and caches, you can, because we use ring buffers, which is the same, it's basically with an offset, it's basically the same architecture as Kafka. We also support, with Kafka, we can also go back. So we can go back 10 seconds, we go back to our snapshot, reload that up on the new node, and then we apply the snapshot and we start reading. Now, if you set your snapshots to longer than the storage capacity of your streaming source, then you could lose data. That's how it works.
What about the data that you've already sent out? Don't you duplicate that?
No, we don't duplicate that. We don't duplicate that. We have at least once. With our at least once guarantee, we will potentially duplicate it. With the exactly once, we do extra checking, so there's no duplication. Don't ask me how it was implemented. I didn't write the code, but you can test it. Okay. Question from the gentleman?
So how do you update the pipeline dynamically
How do we update the pipeline dynamically
in clustering?
in clustering? Can you clarify? Okay, so the question is, how do you dynamically change the pipeline of an executing job? So I'm going to answer this two ways. First of all, if you change the size of this is not what you asked, I think, but it's tangential. If you add extra nodes, the job that's currently running ignores those. It only runs, so if you're running on 5 and you add another 1 or 2, it's ignored. Now, if you want to change the job, you have to start a new job. So a job is, so you would stop the job and then you would fire up a new job. Now you can do that from any node, you can do it client server. When we start a new job, we copy it's an isolated class loader per job. So on each node, we copy all the code that's needed and then we execute it. But we don't support dynamically changing a job during its execution. If you want to change the So a job, we don't support dynamic changes of jobs. Yeah. All right. Well, look, thank you very much, everyone. And jet.hazelcast.org. Look out for point 5. The pipeline API is here. The way we're looking at Jet, we've got a nice following of people using it. We're going to really start promoting it now to our in-memory data grid base, now that we've finished all those integrations, and also now that we've actually finally got an API that's as simple as java.util.stream, but powerful. So there's a few more things to add to Jet, but we're thinking that 0.6, which will be out in February, will be the 1.0 version of Jet. All right, so thanks very much.